Hello everyone, my name is Chirag. Today we are going to talk about traceroute. It's a wonderful and very important utility, especially when you are troubleshooting a network problem or when you want to find out the exact path a particular packet takes from source to destination. It shows you the number of hops uh, from source to destination. IP is a connectionless service, and the path that it takes is not fixed. It keeps on changing. It depends upon your routing. So the trace route is a very important utility that network administrators and all network professionals use. It is very popular. In today's lecture, I'm going to talk about how exactly trace route works. For that, I have demonstrated a very simple topology. This is a 3 router network. I have used Cisco IOS image in GNS3. They are running OSPF as their internal routing protocol. It's a very simple single area uh, design. So everything belongs to area 0. I have used two hosts. One is a Windows PC, showing you as a VM here, XP admin PC, which is a Windows XP system. This host has been integrated into GNS3 by using VMware. Another host, PC1, is a Linux or Unix host. This is part of GNS3. So this VPCS PC1 is already part of GNS3. It has been integrated into GNS3. Wonderful, lightweight host that you can use inside GNS3. Alright, so we will see how exactly traceroute works. Some background information. Uh, we need some information, some knowledge about ICMP and TTL. ICMP is a wonderful TCP/IP layer 4 protocol which is very useful in sending error messages. So whenever a routing device receives receive a packet that it does not know what to do with, it sends an ICMP error message back to the client, back to the source. So it is very useful in any IP network. We also need to understand the purpose of TTL. TTL stands for time to live. It is an 8-bit field in an IP header. So this is an IP header. There is an 8-bit field in an IP header. TTL is basically a loop prevention mechanism. When there is some routing misconfiguration or some problem with routing, a packet goes on and on. It goes round and round in the network endlessly if there is no TTL. So how does TTL work? Every routing device, when it receives a packet, it processes the packet, and before forwarding the packet to the next routing device, it decrements the TTL value by 1. So for example, when R1 receives an IP packet, it with a TTL value set to 64, it processes the packet, decrements the TTL value by 1, the result is 63, and then forwards the packet to, say for example, R2. So traceroute utility basically uses the beauty of TTL values and identifies the number of hops from source to destination. This is how it works. So on an XP admin PC, when you try to trace to, say, this network 192.168.3.1 on R3, you will open a command prompt and you will type traceroute, TRACERT, leave a space, and type 192.168.3.1 and hit enter. This is what happens. Your a packet is created from and with the source of 10.1.0.50 with a destination of 192.168.3.1. Since the destination is not on the local network, the request is forwarded to the default gateway. In this case, the default gateway to the XP admin PC is R1's FA0/1 interface configured with 10.1.0.1. The request reaches here. Now, an interesting thing to note about traceroute is that the first packet is set with a TTL value of 1. So when R1 receives the IP packet, the TTL value is 1. R1 processes the packet, and decrements the TTL value by 1, so the value becomes 0. Now the destination is not right here, so uh, by by norm, if the TTL value is 0, that routing device will not forward the packet to another routing device, it will just discard the packet. So since the TTL becomes 0, it discards the packet, and in the process it sends an ICMP error message back to the source. In this case, R1 sends a time to live exceeded error message back to the source 10.1.0.50, our XP admin PC. That's where the Windows client knows about the first hop, and after that, it sends another packet with a TTL value of 2, in which case the packet is received by R1, the TTL value is decremented by 1, so the result becomes 1, 2 minus 1, and the result becomes 1, and that packet is forwarded to R2. R2 processes the packet, uh, decrements the TTL value by 1. At this point, the TTL value becomes 0. Hence, instead of forwarding the packet, R2 drops the packet and sends an ICMP time to live exceeded error message back to the source, which is our XP admin PC. That's how the XP admin PC knows about the second hop, so on and so forth. We will see how exactly this how exactly this works by using Wireshark. So let's just try to do traceroute using Wireshark. Here is my Windows VM. Let me just clear the screen. Okay, so I'm on 10.1.0.50. Let me confirm the IP address. The IP address is 10.1.0.50 with a /24. In this scenario, we are using /24 bit mask all across, with the default gateway of 10.1.0.1, which is R1. Okay, and we are going to trace to 192.168.3.1. Okay, remember, OSPF routing protocol is in place and routing is working. All the hosts are reachable, so that has already been taken care of. Alright, before I start the trace, I will start the Wireshark capture. In GNS3, when you want to run Wireshark on a specific link, you need to take your cursor to the link, or right click and select start capture. It shows you, are you sure you want to start a capture between the switch port number 1 here and the R1's F0/1 interface. Hit OK, and Wireshark will start automatically, again depending on the GNS version you're using. Alright, my Wireshark is running. I'm going to my XP host and I'm traceroute. The command is tracert, traceroute, because this is basically uh, the history goes back to DOS disk operating system, which had a limitation of 8 characters. Alright, 192.160.3.1, and our trace has started. It will take some time. Let's check the Wireshark capture. Okay. In the meantime, let's try to filter it. So our network topology is right here, and let's do there will be a lot of packets, so let's do the filtering by the destination IP address. When you want to filter in Wireshark, the command is ip.addr is equal to 192.160.3.1. This is how it is going to filter. Okay, let's see what happened to Wireshark. Oops. Alright, our trace is complete. Sorry about that, I had to pause the recording and there was some routing issue that I had to fix. Unfortunately, on this interface on R2, that had been down. That's why my OSPF was broken. It was not working. I forgot to check that. Alright, but everything is done, and well, we can see that our trace is complete. We found 2 hops 10.1.0.1 is our first hop, R1, FA0/1. Let me try to put it side by side for a better view. Okay, and okay, 10.1.1.2 is our second hop, which is R2, and 192.168.3.1, which is our R3's destination, our third hop. Okay, and also note that traceroute sends three similar packets in order to average out the round trip time. So three similar packets are sent in order to discover the first hop. Similarly, three packets for the second. For all the hops, three packets are sent in order to average out the round trip time in milliseconds. Alright, so here is our Wireshark capture, and I will explain what exactly happens in the background. So here in the first packet, the source is this is our very first packet. The source is 10.1.0.50. Our XP admin PC Windows host with the destination of 192.168.3.1 going to R3's interface. Okay, this is an ICMP packet. Now the reason why I have showed two different hosts, so one is a Windows host, the other is a Unix one, is that the behavior of traceroute is different. The traceroute uses ICMP when you use a Windows host, whereas it uses UDP at TCP IP layer 4 when you use a Linux or Unix host. Since I have used traceroute or traceroute from my Windows machine, it uses the protocol as ICMP. This is an echo request, ICMP echo request with the TTL value of 1. So this is the very first packet sent from 10.1.0.50 to its default gateway 10.1.0.1 with the destination IP address of 192.168.3.1. That's our actual destination. The TTL is 1. This packet is received by R1. Since it is a remote network, the packet needs to be forwarded, but R1 as the norm decrements the TTL value by 1, so the TTL becomes 0. Since TTL is 0, the packet cannot be forwarded and hence it is discarded. While discarding the packet, R1 also sends an ICMP error message back to the Windows host. This is a time to live exceeded error message sent from R1 10.1.0.1 to the XP admin PC on 10.1.0.50. That is the very next packet, frame number 25 here. So 10.1.0.1 to 10.1.0.50 is the protocol is ICMP. Error messages are always ICMP. This is a time to live exceeded error message. That's where the Windows XP host knows about its first hop. So two more packets are sent with the TTL value of 1. So this is the first packet. Frame number 26 is the second packet. Frame number 28 is the third packet. That's where we see the averaging out of this. So this is 5 millisecond, 10 millisecond, 9 millisecond. Those were the three packets sent in order to discover the first hop. Then the fourth packet, three packets with a TTL value of 1. The fourth packet is set with a TTL value of 2. As you can see here, TTL is equal to 2 in frame number 47. That packet is received by R1. TTL is decremented by 1, so the result becomes 1 and is forwarded to R2. R2 receives the packet, decrements the TTL value, the TTL becomes 0. Since the destination is not here, it is remote, the packet is discarded and ICMP time to live exceeded error message is sent back to the source. So in this case 47 is the request, first request with the TTL value of 2, and the error message is sent from 10.1.1.2, which is FA0/1 of R2 to our Windows XP host, which is 10.1.0.50. Okay, two more packets are sent with the TTL value of 2. So this is the first packet, second packet, third packet. After total number of 3 packets, the 7th packet is set with the TTL value of 3, as you see here in frame number 68. So that is received by R1. TTL is decremented by 1. TTL becomes 2, forwarded to R2. R2 decrements the TTL by 1. The result becomes 1, is forwarded to R3. R3 receives the packet, decrements the TTL. The TTL becomes 0. However, the destination is not remote. It is right there on R3. Hence, the packet is delivered for processing. In this case, the protocol is ICMP, and the packet is the ICMP echo request. So the reply is ICMP echo reply, as you can see in frame number 69. So this is an ICMP echo reply from the destination. So now source and destination are swapped. Now the source is 192.168.3.1, destination is 10.1.0.50. That is your ICMP echo reply. 3 such replies are sent. That's where we know that our destination is 3 hops away, with the first hop R1, second hop R2, and the third hop R3, your exact destination. That's how it works on Windows systems. Now on Unix or Linux systems, it uses UDP. We will also have a look at that. So let's minimize this and check this out. Okay, so PC1 is VPCS Unix or Linux host, right there integrated into GNS3. It's a part of GNS3. Let me show the IP scheme. Its IP is 10.1.0.60 with the default gateway of 10.1.0.1, which is R1. Okay, since it is an inbuilt Linux host and inside GNS3, the command here is just trace and 192.168.3.1. Let me make sure, let me close this out, and let me make sure our capture is running. I'll stop the capture, start it again. There is our capture, and let me do the trace. There you go. Again, this discovered the same number of hops. The first hop is 10.1.0.1 R1. The second hop is 10.1.1.2, which is R2. The third hop, in this case, it is different. Instead of the destination 192.168.3.1, it is 10.1.2.2 R3, the third hop. Why? We will have a look at it, don't worry. Okay, so these are the 3 hops. Let's stop the capture, and okay, let's try to analyze. So let me just stop the capture here also. Either way you can stop, that's fine. Okay, a lot of packets, I need to filter it. So let me put a filter on it. This time I'm going to put a filter by the source IP address. What's happening? 3.1, similarly 10.1.0 to 60. Interesting. Well, I'm not getting any packets. I'm not getting any packets. Taking the capture again. Okay, let me stop the capture. Not sure why it did not capture the packets in the first place. Okay, I can see the packets now. Okay, that was weird. I was not able to capture any packets. Okay, alright, so this is from a Unix or Linux host, As I said, Linux or Unix uses a UDP. That's what you can see in the frame number 4 for our first packet. So when we try to trace 192.168.3.1 from the Linux host to 10.1.0.60, the very first packet is 10.1.0.60, our frame number 4, with the destination of 192.168.3.1. The protocol is UDP. Remember, when you use a Linux or Unix, the protocol is the UDP and not ICMP. It uses a random high numbered ephemeral port. Here it has chosen 24,865 as a source port, going to 24,866. So that's our first packet that is received by R1, its default gateway, and R1 processes the packet. Here the TTL is 1. It does not show right here in a UDP packet. You need to open layer 3 information, IP version 4, just expand that, and you can see that time to live is 1. And at TCP IP layer 4, the protocol number is 17, which is it uses UDP. When you see an ICMP packet like this, it shows 1, a protocol number 1, which is ICMP. Okay, so the first packet is sent with the TTL value of 1. It is received by R1, TTL is decremented by 1, TTL becomes 0. The destination is remote, hence the packet is discarded, and an ICMP time to live error message is sent back to the client. This is your error message, time to live exceeded. Remember, I told you error messages are always ICMP. So even though the request packet is UDP, the error messages are always ICMP, because that's the responsibility of ICMP to deliver error messages. Okay. Similarly, two more packets are sent. So frame number 6 and frame number 8 are the similar packets. So 3 packets are sent, and their round trip time is recorded. Now the fourth packet, which is frame number 10, is sent with the TTL value of 1. So this frame number 10, if I expand layer 3 information, this is TTL value of 2. Okay, that is sent to R1. R1 decrements the TTL by 1. The result is 1, is forwarded to R2. R2 decrements the TTL by 1. The result becomes 0. The destination is remote, not on this router. Hence, the packet is discarded, and a time to live exceeded message is sent back to the source. Similar, 2 more packets, so in all 3 packets. So this is the first packet with the TTL value of 1, frame number 10. Frame number 12 is the second packet, frame number 14 is the third packet, and frame number 16 is going to be our 7th packet with the TTL value of 3. You can see it here, right here. Okay, and similarly, so that is that packet with the TTL value of 3 is sent to R1. R1 decrements the TTL by 1, it becomes 2, forwarded to R2. R2 decrements the TTL by 1, the result is 1, is forwarded to R3. At R3, it receives a packet with the TTL value of 1. It is decremented by 1, the TTL becomes 0. However, the destination 192.168.3.1 is not removed. It's right there attached to router 3. Hence, the packet is delivered. Now here, the request is UDP. So if you look at this, is frame number 16 with a value of TTL is 3. So we are right packet number 17. Let's look at frame number 17. Now since this is a UDP packet sourced from 24,865 going to 24,866, it will try to reach the destination on that particular UDP port number. Now naturally, a Cisco router is not listening to such a high numbered UDP port. There is no server process running on that port. These are some random ports picked up by traceroute or traceroute utility. So since that port is not open, that port is not listening for that service, the host R3 will send an ICMP error message back to the client stating destination unreachable, port unreachable, and that's why the error message is from this interface. The destination is right here, but since it's not able to open that port on that specific port, this interface, you receive an error message, ICMP error message back from this interface 10.1.0 10.1.2.2. This is the packet capture difference between when you use a Windows host or a Linux host. In the case of a Windows host, since it is able to reach 192.168.3.1 successfully, it gets an ICMP echo reply from this IP address. But in the case of a UDP, it's not able to open that port on this IP address 3.1. That's why this interface 10.1.2.2 sends an ICMP error message back to the source, and in this case our Linux host. So the error message is destination unreachable, port unreachable. You can see the error message in ICMP packet type 3 code 3, destination unreachable, port unreachable, sourced from 10.1.2.2 to our Linux host. And two more packets, so that's where you get to know about this result, the first hop, second hop, and the third hop. And you also see the ICMP error type 3 code 3, destination unreachable, port unreachable error message. Alright, so that was a high level overview. I try to explain as much as I can. Basically, two platforms, Windows and Unix or Linux, and the difference is Windows uses ICMP whereas Linux or Unix uses UDP. Right, I hope I hope you found this video useful. If you have any comments, if you have any suggestions, please share, and I will try to include them in my next videos. Thank you very much for your time. I really appreciate that.